So this chapter is on temperature and heat, and we'll start with temperature. You're probably familiar with the temperature scale, so if I give you and I give you the Celsius scale and the Fahrenheit scale, and maybe the Kelvin scale. So this is 0, this is 32, and this is like 273. I think it's 0.15, but it doesn't matter. This is, of course, at atmospheric pressure. And then for boiling, it's 100 degrees. I suppose it should be 0 degrees, 212 degrees, and this is 373. Notice that the Kelvin scale and the Celsius scale are scaled the same. That is to say, a Kelvin and a Celsius degree are the same. There's 100 between boiling water and freezing water in both cases. And so we can write these things a few ways. We can say, like, the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32 degrees. And we can say, if we reverse that, we can say the temperature in Celsius is equal to the temperature in Fahrenheit minus 32 degrees times 5/9. This is just an algebraic rearrangement of that one. And then we can say the temperature in Kelvin is equal to the temperature in Celsius plus 273. And if you need to go from Fahrenheit to Celsius, to Kelvin, you can rearrange those and do that. And so I can just do an example. If for 100 degrees Celsius to temperature in Fahrenheit, I would say temperature in Fahrenheit, the temperature in Fahrenheit is equal to 9/5 times 100 degrees plus 32 degrees, which is equal to 180 degrees plus 32 degrees, which is equal to 212 degrees. So that's the Fahrenheit temperature that corresponds to 100 degrees Celsius. So you can do as many of those as you want for practice. So let's talk about thermal expansion. So if you take an object and heat it, these are little flames, right? It expands. It can be a piece of wood or a piece of metal or something like that. The reason it expands because when atoms gain thermal energy, they vibrate more, and that causes the object to expand. And so it turns out that the rate of expansion the expansion with respect to temperature, the change in length I would write it this way, is proportional to the length. This is dl dt is the change in length with respect to a change in temperature is proportional to how long it is. Hopefully this makes common sense, sort of. How much expansion you get depends on how long the object. An object that's really short isn't going to have much expansion. An object that's really long is going to have more expansion. And so, assuming they're made out of the same material. And so, you can always change a proportionality into an equal sign by just inserting a constant. So we write it this way. The change in length of an object with respect to a temperature is equal to alpha. So that's a proportional sign for math, and that's a Greek letter alpha. Don't get those mixed up. L. And so this is the proportionality relationship. This is the relationship between the change in length with respect to temperature is proportional to the length, right, to how long the object was in the first place. And so alpha is called the coefficient of thermal expansion. So let me just give you an example. For the Golden Gate Bridge, it's 2 words. The length is 1 to 75 meters. Between winter and summer, temperature change is delta T equals 55 degrees Celsius. In other words, T winter is like minus 15 degrees, and T summer is equal to 40 degrees. And so we want to know the length change, right? And so we had dl dt is equal to alpha L. And so that says that dl is equal to alpha L dt. And so we can approximate this and just call this the change in length. The dl is equal to alpha L times the change in temperature. And we know all these if we assume that the bridge is made of steel. So alpha for steel is 12 times 10 to the minus 6th per degree Celsius. Can you see that on there? Right. And so that means the length change is equal to 12 times 10 to the minus 6th per degree C times 1275 meters times 55 degrees C. And so that comes out to 0.84 meters. That's actually a long bit. That's bigger than this, right? And that expansion has to take place in the bridge. Now the bridge probably has sections that are shorter than 1275, but a lot of expansion has to take place between the winter and the summer on the spans in the bridge, and the bridge has to be designed to account for that, to allow for that. Often, even on overpasses, you'll see things that look like this, like intertwining fingers on the road between the winter and the summer. In the winter they look like this, and in the summer they look like this, to allow the span of the bridge to expand into the supports. Okay. So we said dl dt equals alpha times the length, or we rewrote this as delta L equals alpha L delta T, however you want to say it. And so So how does an area expand, right? An area has to expand. And so if we just take a rectangle, right, and say it's L1 by L2, and we allow it to expand. I should have just made those dotted lines, but you get the idea, right? And so this is delta L2, and this is delta L1, and we say that what we want to say is we want to say, look, d area, d temperature is equal to some quantity beta times the area. And so that means that delta area is equal to beta area delta T. And I want to relate this beta to that alpha. That's kind of my goal here. And so delta area is just it's just the area of the big rectangle over here. So it's L1 plus delta L1 times L2 plus delta L2. Right? That's the area of the big rectangle minus L1, L2. That's the little rectangle, right? The change in area, delta area, is the stuff that's trapped between the dotted lines and the solid rectangle. And that's equal to beta times the area times delta T. And so if you expand this guy out, this is L1, L2 plus L1 delta L2 plus delta L1 L2 plus delta L1 delta L2 minus L1 L2 is equal to beta A delta T. The L's are just lengths, this length or that length. And we know that the lengths expand according to this equation. And so I've got a whole bunch of algebra here, but right away I can say, look, that term cancels with that term. And now we have L1 delta L2 plus delta L1 times L2 plus delta L1 delta L2. And we're going to say, look, this is a calculus argument here. Since delta L is much, much smaller than L, or delta L1 is much, much smaller than L1, and delta L2 is much, much smaller than L2, we're just going to cancel this term out, neglect that term. And we can say in the limit as delta L gets small, this term is negligible with respect to these, because in the calculus type argument, delta L squared is smaller than, is much smaller than delta L. And so this gives me L1 delta L2 plus L2, if I want to write it the other way, L1 equals beta times the area, which is just L1 L2 delta T. Right. And now I'm going to divide both sides by L1 L2, and this gives me delta L2 over L2 plus delta L1 over L1 is equal to beta times delta T. But if I go up to this equation, I'll just write it over here, right? I can say, look, delta L over L is equal to alpha times delta T. And so this is just alpha times delta T, and this guy's just alpha times delta T. And so this becomes alpha delta T plus alpha delta T is equal to beta delta T. Or in other words, beta, the coefficient of area expansion, is just 2 times the coefficient of linear expansion. And so you can just use this formula. You can just say, look, d area, d temperature, is equal to 2 alpha times the area. And so if I write all these down, I would say d area, d temperature is equal to 2 alpha times the area. And then I haven't even done this one, but it works exactly the same way. D volume, d temperature is equal to 3 alpha times the volume. And so once you know the coefficients of thermal expansion, you can do a linear expansion problem, an area expansion problem, or a volume expansion problem without too much difficulty. I'll give you a few alphas. So I'll just write down a few of these: material, and then alpha, and it's 1/degrees Celsius. That's the units for alpha. And so let me give you a few. Aluminum is 25 times 10 to the minus 6. Gold is 14 times 10 to the minus 6. Iron or steel is 12 times 10 to the minus 6. That's probably enough. So if you look at like a liquid doesn't really have a linear expansion, but it has a volume expansion, even though it's just 3 times what the linear expansion would be. And so if I say I could put water here, and I'll put 3 alpha. So if you're using water, you would use the volume expansion coefficient, and so, but it's just going to be 3 times what it would be if there was a linear. This is 210 times 10 to the minus 6. Gasoline is 950 times 10 to the minus 6. That's probably enough. So suppose your 60-liter steel gas tank is full and at 15 degrees C from cool gas kept underground. All right, how much gas spills out when it warms to 30 degrees? So you put gas in your tank, and now it's the gas and the tank are at 15 degrees Celsius. But in the air outside, it warms up to 35 due to the engine and other stuff. And so when that happens, both the gasoline and the tank expand. And so we want to know the difference between those two numbers, right? And so we can say, look, delta V for the tank is equal to 3 alpha V tank delta T. And then similarly, delta V for gas is equal to 3. So I'll call this, since it's steel, I'll call that alpha S, 3 alpha gas. The 3 alpha gas is the number that I put in the table a minute ago. And you don't have to multiply it by 3 because I already gave it the 3 in there, but we'll put that number in a second. V gas delta T. The delta T's are the same, right? Because they both go from delta T equals 35 minus 15, which is 20. Right? And so the volume of the spill is delta V gas minus delta V tank, which is 3 alpha G, I'd write it that way, times V gas times delta T, minus 3 alpha steel V tank delta T. So these two guys are the same, right? They're both 60 liters. It's the alphas that are different. And so this really comes out to the V spill is equal to 3 alpha for gasoline minus 3 alpha for steel, V times delta T, where I can use either V gas or V tank because they're both 60 gallons, so I'll just call it V. Right. And so this is 950 times 10 to the minus 6 per degree C, minus 3 times 12 times 10 to the minus 6 per degree C, times 60 liters times 20 degrees C. When I evaluate that, I get about 1.1 liters. So if you fill your tank up to the very top when it's cold, as it warms up, it's going to leak out gas. Unless you're driving fast enough to burn that off before it warms up.